The center of our galaxy is not quiet. Even now, as you breathe, 26,000 light-years away, a supermassive black hole is stirring, silent, invisible, and immense. Around it, stars move in tight, impossible orbits, circling at thousands of kilometers per second. Clouds of dust drift like ancient smoke. Light bends, time slows, and yet from here, beneath the stillness of your room, none of this motion touches you. The Milky Way turns, its heart beating beneath arms of starlight, but the night sky feels unchanged. It is one of the universe's gentlest illusions, that we live far from danger, far from gravity's deepest well, when in truth, we orbit its pull every day. Tonight, we'll drift inward, slowly, calmly, toward that hidden center, tracing how stars survive there, how matter collapses, and why our galaxy carries a dark heart that shapes everything we see. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm explorations alive, and I hold your support with real gratitude. Now we drift into part 1. Part 1. What exactly lies at the Milky Way's center? At the heart of our galaxy, hidden behind dust, gas, and 100 billion stars, sits a region so dense and so bright in radio waves that astronomers once struggled to believe it was real. For decades, the center of the Milky Way was only a direction on a map, Sagittarius A, a point our instruments whispered about but never clearly saw. Only in the last few decades did we uncover the truth. A supermassive black hole, 4 million times the mass of the Sun, resting in perfect darkness, shaping the galaxy around it. If you could drift through space without the interference of dust or light, if you could slide between the stars with no friction, no noise, you would eventually reach this hidden place. From afar, nothing marks it. There is no swirling beacon, no glowing vortex, no spiral funnel like the dramatic paintings often suggest. The center of the Milky Way does not announce itself in visible light. Instead, it hides, shrouded in dark clouds of interstellar dust that have lain across our line of sight for millions of years. To your eyes, it would look like a silent patch of sky. But to the instruments that can see deeper, to radio telescopes, infrared observatories, and X-ray detectors, this region is anything but quiet. For most of human history, the galactic center was unknowable. Ancient civilizations mapped constellations and traced the pale river of the Milky Way across the night, but they could not see its core. Even with the invention of telescopes, visible light was not enough. It wasn't until the mid-20th century that something unusual was detected. A powerful source of radio waves in the direction of Sagittarius. It flickered. It pulsed. It seemed compact, smaller than a star, but brighter, stranger, unlike anything else nearby. Astronomers named it Sagittarius A, the asterisk added by scientist Robert Brown to mark its unusual and energetic nature. But they still had no idea what it truly was. To approach the answer, scientists had to learn to see differently. Infrared light, which passes through dust far more easily than visible light, revealed a dense, chaotic cluster of stars orbiting around something massive yet invisible. These stars were not wandering randomly. They followed smooth, elliptical paths, the unmistakable signature of a gravitational center. Each orbit was a clue. Each curve was a measurement, and as data accumulated, one truth became undeniable. The object at the core had to be incredibly massive. Millions of solar masses compressed into a region no larger than our solar system. No star, no cluster, no ordinary object could match that density. Only one thing in the universe has such power while remaining unseen: a black hole. A supermassive black hole forms when matter collapses under its own gravity to such an extreme degree that nothing, not even light, can escape. Time slows near it, space bends around it, and yet from a distance it can look like nothing at all. No surface, no edge, only a quiet, dark presence. But the region around Sagittarius A is anything but dark. Gas, dust, and even entire stars feel its pull. As matter spirals inward, it heats up, radiating energy across the electromagnetic spectrum, radio waves, infrared light, X-rays. These signals reveal the invisible, and over time, they drew a picture of the galactic center, a crowded, hot, restless core where gravity dominates everything. The closest stars, called the S-stars, move at unimaginable speeds. One of them, S2, completes its orbit in just 16 years. At its closest approach, it travels at more than 7,000 kilometers per second. The fastest of these stars move even quicker. They trace loops around Sagittarius A with perfect precision, as though following a path written into space-time itself. Their motion is our most direct evidence of the black hole's mass. No other object could hold them in such tight, controlled orbits without tearing them apart. No cluster of stars could mimic the grip required. No exotic theoretical object, no boson star, no compact mass matches the density the data demands. Sagittarius A is real, and it is immense. Yet, ironically, it is faint. Compared to black holes in other galaxies, ours is quiet, almost shy. Many massive black holes feed ravenously, consuming gas at high rates, igniting bright disks of light visible across the cosmos. But Sagittarius A consumes very little. Most of the gas that approaches it does not fall in. Instead, it is heated, stirred, pushed away by magnetic fields and turbulence before it ever reaches the event horizon. Our black hole appears to be in a long period of stillness, a sleeping giant resting between meals. But there is evidence that it was once more active. Echoes of ancient flares appear in the reflected glow of nearby gas clouds. X-ray and gamma-ray signals ripple through the region like distant thunder. The vast Fermi bubbles, colossal lobes of energetic particles rising above and below the galactic plane, may be remnants of a powerful outburst millions of years ago. Sagittarius A may be calm today, but it carries a memory of brightness, of motion, of activity far greater than we witness now. To understand this region, imagine descending through layers of increasing density. At thousands of light years out, stars orbit calmly. At hundreds, they begin to cluster. At tens, the environment becomes crowded. Stars drift closer. Gas clouds thicken. Gravity sharpens. Everything starts to move faster. And then, in the innermost parsec, motion becomes extreme. Temperatures rise. Magnetic fields twist. Stars form in strange conditions. Some are flung outward at blistering speeds, hypervelocity stars launched by the gravitational slingshot effect of the central black hole. The closer you move, the more the rules change. Space curves, time stretches, light bends around invisible contours. If you could approach Sagittarius A safely, the view would feel distorted. Stars would streak along warped paths. Light would stretch into deep red hues as it climbed out of the gravitational well. You would feel as though the universe itself were leaning inward, drawn toward a center that pulls on everything, yet reveals nothing. And at the heart of it all, the event horizon, the boundary beyond which all information is lost, not a surface, not an object, but a threshold, the edge of knowable physics. In 2022, humanity saw its shadow for the first time. The faint glowing ring reconstructed by the Event Horizon Telescope. A blurry circle, a dark interior, the closest image we've ever taken of gravity at its strongest. It confirmed what decades of observations had whispered, that the center of the Milky Way is a place where space-time folds inward, where motion becomes destiny, where light itself bows to gravity. And yet, for all its power, Sagittarius A does not dominate our daily lives. From Earth, its pull is negligible compared to the stars and gas around us. We orbit the Sun. The Sun orbits the galactic center. The black hole's influence is vast but gentle, guiding the galaxy rather than consuming it. This is the quiet truth. The Milky Way's center is both distant and intimately connected to everything we see. Without that anchor, the galaxy's spiral arms would drift, stars would wander, the structure of the Milky Way would lose its shape. The black hole is not merely a point of darkness, it is the gravitational heartbeat of our galaxy. And as we continue this slow journey inward, one question remains softly waiting. If this is the anchor of the Milky Way, how do we pierce the darkness that hides it from view? Now we drift into part 2. Part 2. How do we see through the darkness of the galactic core? The center of the Milky Way is buried beneath vast curtains of dust, so dense that visible light cannot pass through. To look inward, astronomers had to shift to gentler messengers: infrared light, radio waves, and X-rays. Using these signals, telescopes on Earth and in orbit began tracing faint arcs of starlight bending through dust. Slowly, the hidden structure of the galactic center emerged, revealing a crowded, hot, restless region we could finally observe with calm precision. If you look toward the galactic center with your eyes alone, all you'd see is a dark river running through the Milky Way's glow. For generations, astronomers stared at this void with frustration, believing very little lay behind it, perhaps a cluster of distant stars, perhaps nothing of significance at all. The visible spectrum, the narrow slice of light our eyes evolved to detect, was blind here. Dust grains only thousandths of a millimeter across blocked it completely, scattering and absorbing the photons before they could reach us. Yet the darkness was an illusion. Behind those clouds lay one of the busiest, most extreme regions in our galaxy. To see it, scientists needed to learn to look in wavelengths our eyes cannot sense. Light, after all, is not one thing. It is a spectrum, a continuum of waves from long and gentle to short and fierce. Visible light is only a sliver. Beyond red lies the infrared. Beyond violet lie X-rays. And farther still, radio waves gently roll through space, carrying information over vast distances. The first glimpse beneath the dust came from radio astronomy in the mid-20th century. Radio waves, with their long, patient wavelengths, slip effortlessly through dust. They do not scatter, they do not dim. They pass through like sound passing through fog. When early radio telescopes swept across the sky, something extraordinary appeared in the direction of Sagittarius. A bright, compact radio source, flickering, warm, persistent, a signal unlike any known star. This was Sagittarius A, though no one yet understood what it meant. As radio astronomy matured, instruments became more precise. Interferometers, arrays of telescopes working together as one, were built across continents. They revealed structure inside the glow, jets, arcs, and knots of energy. Even then, the view was still rough, like trying to see through a frosted window. But for the first time, scientists knew that the darkness was filled with movement. Infrared light provided the next breakthrough. Infrared wavelengths are longer than visible ones, and they weave through dust with far less resistance. When infrared telescopes were pointed toward the galactic center, the dark void burst into life. Thousands, then tens of thousands of stars appeared, dense clusters, crowded orbits, objects swirling around something invisible and immovable. It was infrared observations that allowed astronomers to trace the orbits of the S-stars, the fast-moving stars that whip around Sagittarius A at incredible speeds. These stars became nature's tracers, drawing the shape of gravity itself. Without infrared, they would remain completely hidden, swallowed by dust. But infrared telescopes had a limitation. Earth's own atmosphere emits infrared radiation, blurring the view. So astronomers climbed higher. Observatories were built on mountaintops in Chile, Hawaii, and the Canary Islands. Then, the next step arrived, placing telescopes above the atmosphere entirely. The Spitzer Space Telescope, launched in 2003, spent 16 years capturing the galactic center in crisp, undisturbed infrared light. For the first time, humanity saw the core of the Milky Way as a glowing, tangled web of stars, gas streams, and orbiting clusters, a place more alive than any region near Earth. Still, the deepest secrets remained hidden. To reveal the hottest, most energetic processes in the core, flares from Sagittarius A, shockwaves and gas clouds, the violent births and deaths of stars, astronomers turned to X-rays. X-ray light can only be produced by the most extreme environments, where particles collide at enormous speeds or matter heats to millions of degrees. It does not linger or drift, it blasts. Earth's atmosphere blocks X-rays entirely, so telescopes had to orbit above it. NASA's Chandra X-ray Observatory, launched in 1999, became one of the most important tools ever built for studying the galactic center. Chandra pierced the darkness and revealed a sky filled with violent activity. It showed knots of high-energy gas near Sagittarius A's. It captured rapid flares from the black hole itself, brief, explosive bursts that brightened and faded in minutes. These were not steady, gentle signals. They were the heartbeat of the core. Later, the New Star telescope added even higher energy X-ray vision, revealing structures of matter accelerating through magnetic fields near the black hole. When combined with radio and infrared observations, the galactic center transformed from a dark patch to a layered, multi-dimensional landscape. Each wavelength told a different story. Radio waves revealed swirling gas and magnetic arcs. Infrared light unveiled stars in their orbits. X-rays exposed violent flares and hot plasma. Together, they formed a portrait, but seeing clearly required something even more precise. The inner region of the Milky Way is so compact and crowded that even powerful telescopes need help resolving details. This led to one of the most elegant innovations in astronomy: adaptive optics. Adaptive optic systems use lasers fired into the atmosphere to measure turbulence in real time. Computers then adjust the telescope's mirrors hundreds of times per second to counteract that distortion. Before adaptive optics, infrared images of the galactic center resembled smears. With adaptive optics, they became sharp enough to trace individual stars, watch them move, and calculate their orbits with exquisite accuracy. It was adaptive optics that allowed scientists in 2002 to watch S2 make its close, approach to Sagittarius A, confirming, beyond all doubt, the existence of a supermassive black hole. As our tools improved, the picture grew deeper. Massive surveys like the Vista Variables in the Via Lactea project mapped millions of stars near the core. The Herschel Space Observatory traced cold dust structures. ALMA, the Atacama Large Millimeter I Submillimeter Array, captured the swirling gas disk around Sagittarius A with unprecedented clarity. All these methods, all these wavelengths, all these instruments, together, pulled back the curtain. And then came the most ambitious attempt of all. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, a glowing ring with a dark center, the silhouette of the event horizon. This was not taken with visible light. It relied on radio waves gathered by telescopes across the Earth, synchronized to act as a virtual instrument the size of our entire planet. Only such a colossal lens could resolve the tiny shadow cast by a black hole 26,000 light-years away. The image was blurry by human standards, but profound by scientific ones. It revealed the shape of space-time itself around the black hole. It showed that the theory held. It proved we were seeing gravity at its most extreme. Today, when we look toward the galactic center, we see not darkness, but a layered, living structure, a place of motion, heat, and gravity unfolding across every wavelength of light. What was once invisible is now mapped, measured, and monitored with extraordinary precision. But the dust still lies there, quiet and lightless, blocking our eyes. Only our instruments, our extensions into light we cannot see, slip through those curtains. And as we continue this quiet journey, one question rises from the glow. If we can now see the galactic center, what forces guide the stars that orbit so close to the darkness? Now we drift into part 3. Part 3. Why does a supermassive black hole sit at the core of our galaxy? Almost every large galaxy we've ever studied carries a black hole at its heart. No one fully knows why. Some theories suggest they formed from collapsing clouds in the early universe. Others say they grew from the remains of the first gigantic stars. But in our galaxy, Sagittarius A has become an anchor of motion, its gravity quietly holding the inner stars in orbit, shaping the Milky Way's central bulge like a sculptor working in silence. When you picture a black hole, you might imagine something violent, a cosmic monster devouring anything that wanders too near. But the truth is softer, quieter. Black holes are not engines of destruction. They are consequences of gravity, the natural endpoints of matter pushed past its limits. They form when mass collapses under its own weight, not out of hunger or intention, but out of inevitability. and in the early universe, that inevitability may have been everywhere. To understand why one sits at the center of the Milky Way, we must journey back to a time long before our galaxy existed. The early universe was dense, thick with matter, energy, radiation, and turbulent clouds that stretched across light years. In those chaotic epochs, small irregularities, patches of slightly higher density, began to grow. Gravity fed on imbalance, pulling matter inward, shaping the first stars and proto-galaxies. Some of these stars were enormous, hundreds of times more massive than the Sun. Their lifespans were brief but extraordinary. When they died, they collapsed directly into black holes, each dozens or hundreds of solar masses. These early black holes were seeds, small compared to what would come, but heavy enough to influence the matter around them. As galaxies formed, they collided and merged. Each merger stirred turbulence, sending shock waves through gas clouds, collapsing some regions further while dispersing others. In these environments, black holes did not drift aimlessly. They gravitated toward the densest regions, slowly sinking to their galaxy's center. If the merging galaxies each carried a central black hole, those black holes spiraled inward toward each other, eventually combining in bursts of gravitational waves. Over billions of years, these mergers built the supermassive black holes we observe today, millions or billions of solar masses resting in the centers of most galaxies like quiet anchors. Sagittarius A is one of them. But a deeper question remains, not just how these black holes grew, but why galaxies seem to require one. When astronomers look across the universe, they find a remarkable trend. The mass of a galaxy's central black hole correlates closely with the mass of its bulge, the bright central region where stars cluster tightly. This relationship is known as the M-sigma relation. It suggests that galaxies and their black holes do not evolve separately. They grow together, influencing each other in subtle, profound ways. No one fully understands the mechanism, but the patterns are unmistakable. When the black hole grows, the galaxy grows. When the galaxy forms new stars, the black hole's activity increases. Their histories are intertwined, as if they are partners in a long cosmic conversation. One theory suggests that supermassive black holes regulate star formation. When a black hole feeds, pulling gas into its swirling accretion disk, it releases enormous energy. This energy can heat surrounding gas or push it outward, reducing star formation for thousands or millions of years. The galaxy breathes with the black hole's rhythm, feeding, heating, cooling, forming stars, feeding again. Another idea focuses on angular momentum. Galaxies spin, their stars orbiting the center like particles in a vast whirlpool. Without an anchor, a massive central object, this motion could become unstable, gradually dispersing the galaxy's structure. A central black hole provides a gravitational anchor, a dense point that stabilizes the orbits of millions of stars. But perhaps the most elegant explanation is the simplest. Black holes grow where matter flows. The center of a forming galaxy is the densest region. Gas collects there, stars form there, collisions happen there. Gravity becomes deeper, steeper, more intense. In such a place, collapse is not a question of if, but when. A supermassive black hole may be the natural outcome of having too much matter in too small a space. Sagittarius A likely began as a much smaller object, maybe a black hole formed from an early supernova, or a primordial collapse, or a merger of several stellar mass black holes. Over billions of years, it grew by absorbing gas, stars, and smaller black holes drifting inward. It grew slowly compared to the monsters at the centers of quasars, those brilliant, ravenous black holes that outshine entire galaxies, but it grew steadily enough to anchor the Milky Way. But the strangest truth is this: Sagittarius A is not currently feeding. The black hole at the center of our galaxy is unusually quiet. Most of the gas that approaches it is deflected or heated and flung away before crossing the event horizon. It brightens occasionally, flaring in X-rays and infrared light, but these outbursts are brief, minutes to hours, suggesting it is nibbling, not feasting. Yet its quiet nature is perhaps why the Milky Way looks the way it does. In galaxies where the central black hole feeds aggressively, jets of energy can blast outward, clearing gas and halting star formation. These galaxies often become elliptical, smooth, featureless, and red. The Milky Way, by contrast, is still vibrant. It has spiral arms, ongoing star formation, and gentle structure. Sagittarius A does not dominate its surroundings with violence. Instead, it holds the inner galaxy together with a soft, steady pull. Some astronomers propose an even more intriguing idea, that supermassive black holes might actually help galaxies form in the first place. In computer simulations of the early universe, galaxies often fail to grow realistic shapes unless a central black hole is included. Without it, gas cools too quickly and forms too many stars in the wrong places. The presence of a central black hole, even a small one, slows this collapse, allowing spiral arms and bulges to form more naturally. In this picture, the black hole is not an afterthought. It's a crucial ingredient in galactic architecture. Picture the Milky Way as a vast, rotating city of stars. Roads of gas spiral inward. Clusters drift through neighborhoods of light. In the center lies a massive invisible hub. It does not shout, it does not glow, but everything orbits its presence. It shapes the flow of matter, determines the pace of rotation, and stabilizes the entire disk. This is the role Sagittarius A plays. It is sometimes easy to forget that black holes are not holes at all. They are objects, dense, compact, and physical. They distort space around themselves. They slow time. They sculpt the gravitational landscape. In the heart of our galaxy, the gravitational field is a steep, elegant slope leading inward to Sagittarius A. Without it, the orbits of the inner stars would unravel. The central bulge would puff outward. The spiral arms might drift or warp over billions of years. With it, the Milky Way remains coherent, structured, graceful. Astronomers once wondered whether galaxies formed first, with black holes appearing later, or whether black holes formed and galaxies grew around them. Today, the evidence suggests something more nuanced. They formed together, each influencing the other in ways we still don't fully understand. Sagittarius A is both ancient and central to our existence, not because it performs dramatic acts, but because its steady gravity holds the inner galaxy in place. It is the silent heart of the Milky Way. And as we continue drifting inward, one question begins to rise. How do stars orbit so close to something so powerful, and why do they survive? Now we move quietly into Part 4. Part 4. How do stars orbit so close without being torn apart? Near the galactic center, a small cluster of stars moves in orbits tighter and faster than anywhere else in the Milky Way. One of these, known as S2, completes a full orbit in just 16 years, whipping around the black hole at over 7,000 kilometers. Each star is a test of gravity, tracing perfect curves through warped spacetime. Their survival seems impossible, yet they follow stable paths, balanced on the knife edge between motion and collapse. To understand how these stars endure such extreme conditions, imagine drifting inward through the inner few light-years of the Milky Way. The serene spiral arms give way to a crowded, restless core. Stars no longer float through vast empty stretches of space. Instead, they move like dancers packed onto a tight stage, each orbit influenced by the gravitational pull of thousands of neighbors. As you glide closer to Sagittarius A, the stellar density rises dramatically. Here, the average distance between stars shrinks from light years to light months, sometimes even light weeks. And yet, amid this claustrophobic environment, something remarkable happens. Order emerges. The stars closest to Sagittarius A, known as the S-star cluster, do not drift wildly. They do not collide in chaotic bursts of heat and light. They form a family of precise, stable orbits, each one tracing a path predicted almost flawlessly by Einstein's general relativity. Their motion is fast, but it is not frantic. It is smooth, controlled, and deeply governed by geometry. This stability begins with the same principle that keeps planets orbiting the Sun: velocity. A star moving fast enough can avoid being pulled inward, even when orbiting near a black hole. Gravity pulls it in, yes, but the star's sideways motion carries it forward at the perfect speed to fall around the black hole rather than into it. This is the essence of an orbit, falling forever, but always missing the center. Closer to a black hole, the required balance becomes extreme. To survive a pass just a few astronomical units from Sagittarius A, S2 must travel at a blistering speed, faster than most stars anywhere in the galaxy. If it were slower, it would spiral inward and vanish. If it were faster, it would break free and escape into the outer galaxy. It must maintain an exquisitely narrow range of velocity, tuned to gravity's exact strength. And it does. But this alone doesn't explain how these stars avoid tidal disruption, the stretching force caused when one side of an object is pulled harder than the other. Near a black hole, this effect can be fatal. A star that wanders too close can be ripped apart in a spectacular event known as a tidal disruption flare, where the star's matter is shredded into a glowing stream of plasma. So why don't the S stars meet this fate? The answer lies partly in distance. Even the most daring of these stars do not cross the event horizon or plunge deep into the region where tidal forces become overwhelming. They pass close, but not close enough for the black hole to overcome their internal gravity. A typical star like S2 is dense enough and its orbit wide enough that the tidal force it experiences at nearest approach, while immense, is still weaker than the force holding the star together. But gravity alone cannot explain the persistence of order so close to a 4 million solar mass singularity. The stars also owe their survival to something quieter, the smoothness of space-time around them. Einstein taught us that gravity is not a force, but a curvature. Objects follow the straightest possible paths through a curved geometry. Near a black hole, those paths bend sharply, but they are still predictable. As long as a star begins its journey with certain velocities and directions, its orbit will remain stable for thousands, even millions of years. The S stars are trapped in these gravitational grooves, natural pathways carved into space-time. Like marbles rolling along a curved bowl, they follow the contours of the geometry around the black hole. This is why their orbits, though fast, are not chaotic. They obey the laws of geodesics, the natural trajectories through curved space-time. Still, a question lingers. How did these stars arrive here in the first place? How did such young, massive stars end up in one of the most hostile gravitational environments in the Milky Way? Many astronomers believe they were not born where they now orbit. Star formation is difficult near a black hole. Tidal forces stretch clouds of gas, preventing them from collapsing into new stars. Yet the S stars are young, only a few million years old, far younger than the black hole they orbit. This contradiction is known as the paradox of youth. One solution is that the S stars were formed farther from the black hole, in dense clusters where star formation is possible. Over millions of years, gravitational interactions nudge them inward. Each close encounter with another star or cluster slowly exchanged momentum, causing the stars to migrate toward the galactic center like pebbles rolling toward the lowest point of a bowl. Another theory proposes a more dramatic origin. Some astronomers suggest that the S stars once belonged to binary systems, pairs of stars orbiting each other. If such a system wandered close to Sagittarius A, the black hole could rip the pair apart. One star would be flung outward at incredible speeds, becoming a hypervelocity star. The other would be captured into a tight orbit around the black hole, settling into the family of S stars we observe today. This process is known as the Hills mechanism, named after astronomer Jack Hills, who first described it. If true, it would mean that some of the fastest stars in the galaxy, those hurtling toward intergalactic space, owe their motion to the same gravitational encounters that trapped the S stars in their tight, elegant loops around Sagittarius A. The S stars do more than simply survive near the black hole. They reveal its shape. When the star S2 made its closest approach in 2018, astronomers observed something extraordinary. Its light stretched into red wavelengths exactly as general relativity predicted. Time itself slowed near the black hole, and the star's orbit precessed, the point of closest approach shifting over time, not due to Newtonian mechanics, but due to the curvature of space-time. This was one of the clearest tests of relativity ever performed around a supermassive black hole. The S-stars, by merely existing, became instruments of measurement, silent probes tracing the contours of gravity. Their precision is astounding. Each orbit reveals how mass is distributed within the central region. If dark matter were abundant there, or if Sagittarius A were something other than a black hole, a cluster of exotic particles, for instance, the orbits would deviate from current predictions. So far, they have not. The stars confirm the presence of a compact mass exactly where the black hole must be. Their motion is the universe's handwriting. As you imagine yourself drifting among these stars, picture a sky brighter than any desert night on Earth. Picture points of light streaking along curves too fast for the mind to grasp. Picture the calm silence of a region where every motion is governed by the geometry of gravity. None of these stars feel their speed. None feel the violence of their surroundings. They move in perfect freefall, weightless, gliding along the contours of space-time. What to us seems precarious feels to them like rest. And yet, there is an edge to this serenity. One misstep, one gravitational nudge from a passing star, one collision with an unseen object could alter a star's orbit enough to send it spiraling inward. The knife-edge balance they maintain is real. Still, over millions of years, they persist, not because they defy gravity, but because they obey it with profound precision. And as we continue deeper into this hidden core, a quieter question emerges. If stars can dance so close to the darkness, what happens to matter that ventures even closer? What becomes of the gas and dust that do not escape the black hole's pull? Now we drift into Part 5. Part 5. What happens to time near a black hole? Closer to Sagittarius A, time itself begins to slow, not metaphorically, but physically. General relativity predicts that clocks tick more slowly in stronger gravity, and near the galactic center, that effect becomes profound. If you could drift close to the event horizon and return, you would come back to a future that has moved on without you. Time bends there, not as a thought, but as a measurable truth carved into the fabric of space-time. To understand this slowing, imagine holding two clocks, one kept safely here on Earth, the other lowered slowly toward the supermassive black hole at the Milky Way's center. As the second clock descends, its hands begin to lag. At first, the difference is imperceptible, a fraction of a second. But as the clock nears the event horizon, the lag deepens. Minutes stretch, hours distort. A day near the black hole could pass with only moments ticking by for your clock at home. And at the brink of the event horizon, the distant clock appears to freeze entirely, trapped in a moment it will never escape. This isn't science fiction, nor is it an illusion. It is the geometry of space-time itself. Einstein's general relativity shows that mass curves space-time, and the deeper the curvature, the slower time flows relative to regions where space-time is flatter. A black hole is a place where curvature becomes extreme, not because of a force, but because the very shape of the universe twists inward, funneling the flow of time toward its center. Near Sagittarius A, this effect becomes more than theoretical. It becomes measurable. Astronomers have observed the star S2 slowing in time during its closest approach to the black hole. In 2018, when S2 passed within 120 astronomical units of Sagittarius AI, instruments detected its light stretching into redder wavelengths, evidence that time was running slower for the star than for observers on Earth. It was the first direct confirmation of gravitational redshift near a supermassive black hole, a real slowing, a real bending of time. From afar, this difference is subtle, but up close, it becomes overwhelming. Imagine that you, aboard a quiet, drifting spacecraft, move toward the edge of the event horizon. Inside the cabin, nothing feels unusual. Your heartbeat stays steady. Your watch ticks normally. Your breathing remains slow and calm. Time, in your own frame of reference, behaves exactly as you expect. But to someone watching you from a safe distance, say, orbiting thousands of kilometers away, your movements begin to stretch. Your gestures take longer. Your voice, if transmitted to them, deepens and slows. Even the light bouncing off your spacecraft arrives later, dimmer, more stretched. Time does not merely slow, it stretches like taffy pulled thin. And this duality is the heart of relativity. Time never feels distorted to the person experiencing it. It is only relative to the observations of another. In your frame, everything is normal, but to the outside universe, your time becomes a shadow of itself. This slowing is not limited to clocks or mechanical devices. It affects everything: your heartbeat, your thoughts, your aging, the decay of atoms, the oscillation of photons. Every physical process becomes slower compared to the rhythm of the wider universe. Yet it is still time, still your time. It is simply running in a different lane of the cosmic track. The closer you drift toward the event horizon, the boundary beyond which no signal can return, the more intense the effect becomes. The event horizon is not a wall, it is a threshold in space-time where escape velocity equals the speed of light, and at this threshold, for an external observer, time appears to stop altogether. To them, you would hover at the edge forever, your image gradually dimming, your signals stretching to lower frequencies. You become an after-image frozen in fading red light. But, in your own frame, nothing special happens at the horizon. No wall, no barrier, no sudden change. You simply glide across, and the universe outside rushes forward in time as though fast-forwarded. Stars evolve, galaxies drift, eons pass in moments. The future unfolds at impossible speed. This is the strange duality of black hole time, stillness and motion coexisting. What is happening beneath these distortions is even more profound. Gravitational time dilation is directly tied to energy. The gravitational potential near Sagittarius A is so deep that time itself is stretched by that depth. Imagine the universe as a landscape carved of hills and valleys. The deeper you go into the valley of gravity, the slower time flows. A black hole is the deepest valley in this landscape, the place where the floor drops away entirely, where space-time falls inward faster than light can climb out. And so, time slows not because clocks malfunction or because physics changes its mind, but because space-time itself is contorted into a shape that elongates each passing moment. Consider how this affects the stars near the black hole. S2, racing through the curvature, experiences time differently than Earth does. Its orbit does not repeat identically from year to year. It precesses, shifting by tiny degrees as relativity distorts its path. The very geometry of its orbit is stretched and twisted by the time-slowing effect of the black hole. Even light is not immune. Photons climbing out of the black hole's gravity well lose energy, which lowers their frequency. They shift toward red. This gravitational redshift is not just a consequence of motion, but of time dilation itself. Light becomes a direct measurement of time's flow, and this truth extends beyond Sagittarius A. GPS satellites must correct for gravitational time dilation to provide accurate positioning on Earth. Clocks placed a few centimeters higher than others tick measurably faster. Time dilation happens everywhere, just most dramatically near the center of our galaxy. If you could hover very close to Sagittarius A without crossing the event horizon, your experience of time would be radically different. A decade might pass on Earth in the time it takes you to blink. If you returned home, you would find a world changed by time you did not experience. This is not a fantasy. It is a reachable future in a relativistic universe. Time itself is elastic, stretching and compressing across gravitational landscapes. And near a black hole, those landscapes transition from gentle hills to near vertical cliffs. But time dilation has one more consequence, one that brings a quiet, sobering truth. For anything falling into the black hole, the journey inward is one way. In its own frame, it crosses the horizon in finite time, but to the universe outside, that moment never arrives. The object becomes a fading ghost at the edge, a memory that stretches into infinity. From the outside, nothing ever fully enters. From the inside, everything continues without pause. Black holes create a boundary between two versions of time. One can be observed, one cannot. Both exist, both are real. And Sagittarius A, our galaxy's anchor, quietly shapes time for everything within thousands of light years, creating subtle variations in the way stars age, the way gas moves, the way light bends. As we drift farther into this cosmic heart, a new question begins to rise softly from the curvature itself. If time bends so dramatically near the black hole, what happens in the environment around it, where gas, dust, and magnetic fields collide in restless waves? Now we move into Part 6. Part 6. Is the galactic center violent or strangely calm? You might imagine the heart of a galaxy as turbulent and explosive. Yet oddly, Sagittarius A sleeps more than it feeds. Most of the time it glows softly in radio waves, quietly collecting drifting gas. But sometimes, perhaps a few times per day, it flickers. Bright flares erupt as matter spirals closer, heating to millions of degrees before falling into darkness. The region is both peaceful and restless, serene yet unpredictable. To understand this strange coexistence of quiet and chaos, imagine drifting toward the galactic center from far outside the spiral arms. For tens of thousands of light years, the Milky Way feels gentle. Wide arcs of stars, soft clouds of gas, dust lanes sweeping gracefully like brushstrokes. But deep in the core, the landscape changes. Gravity thickens. Light bends around dense clusters of stars. Temperatures climb. Yet even here, amidst the crowded heart of the galaxy, the black hole at the center remains surprisingly subdued. Sagittarius A is not like the supermassive black holes found in distant galaxies, whose accretion disks blaze so brightly they outshine trillions of stars. It is quiet, almost hesitant. It consumes matter slowly, reluctantly, as though dozing between long intervals of activity. Astronomers describe it as underfed, a black hole that receives only the thinnest trickles of gas drifting inward from the surrounding environment. Most galaxies with supermassive black holes go through energetic phases, quasar epochs, when their cores ignite with violent luminosity. Our galaxy, by contrast, appears to be in a period of deep rest. The accretion rate of Sagittarius A is astonishingly low. It takes only a tiny amount of matter, perhaps the mass of a small asteroid, each day. Compared to other black holes of its size, this is barely a whisper. Yet this softness hides an underlying tension. As gas approaches the black hole, it does not drift peacefully inward. It collides with other gas, compresses, heats, and interacts with twisted magnetic fields. Even a small stream of matter can create turbulent eddies, shock waves, and arcs of radiation. This is where the region becomes restless. A small amount of matter falling close to the event horizon can erupt into a flare of X-rays and infrared light, bright enough for telescopes across Earth to detect. These flares last only minutes to hours, but they reveal the violent physics at work. The gas near Sagittarius A reaches temperatures of tens of millions of degrees. Electrons spiral along magnetic field lines, emitting waves of energy that ripple through space. Then, as quickly as the flare appears, it disappears. The black hole falls silent again, returning to its soft glow. It is a cosmic heartbeat, quiet most of the time, punctuated by bursts of activity. But the region surrounding Sagittarius A is far from empty. The central parsec, the inner few light years, contains tens of thousands of stars. Some are old, some are massive and young. Some orbit so quickly they trace tight ellipses around the black hole every few years. Their combined radiation fills the galactic core with a luminous haze. These stars create a strange kind of weather near the black hole. Powerful stellar winds collide with each other, sending shock waves through the gas. The winds from massive stars can strip material from nearby objects, creating streams of matter that drift inward. Clouds of dust collide and compress, generating infrared glow. Yet, through all this, the black hole remains mostly indifferent, accreting only a small fraction of the matter that flows past it. Why? In a galaxy core, gas does not fall straight into a black hole. It carries angular momentum, it spins, and that spin prevents matter from simply collapsing inward. Instead, gas tends to circle the black hole, forming a sparse, unstable disk that slowly trickles inward over long timescales. Much of the gas is blown outward, again by heat or magnetic turbulence, before it ever reaches the event horizon. In essence, the black hole's hunger is limited by the chaotic environment around it. This competition between inflow and outflow is one of the reasons the galactic center feels both tranquil and volatile. On large scales, very little changes from year to year, but on small scales, matter dances in and out of gravitational influence, generating flickers, shocks, and bursts of radiation that light up the region with unpredictable beauty. And while the black hole itself sleeps, the surrounding stars create their own drama. Massive stars, some dozens of times the sun's mass, burn brightly and fiercely. They emit intense ultraviolet radiation, stirring the gas around them. Their powerful winds collide, creating arcs of high-energy plasma. And when these stars end their lives, they do so in spectacular supernova explosions. These outbursts carve bubbles into the surrounding medium, enrich the region with heavy elements, and send shock waves rolling across the galactic core. Yet the black hole, patient and ancient, remains undisturbed. Above and below the center, stretching tens of thousands of light years, lie the Fermi bubbles, vast lobes of energetic particles expanding outward. These enormous structures likely formed millions of years ago during a much more active period in Sagittarius A's history. They are remnants of a long-ago eruption, like smoke drifting upward from a fire that has since cooled. These bubbles are proof that the galactic center has not always been quiet. In the distant past, Sagittarius A's may have been far more energetic, perhaps even rivaling quasars in brightness. At that time, its accretion disk would have glowed fiercely, blasting radiation into the galaxy and sending winds of hot gas outward. But now, in cosmic terms, the black hole is dormant, with only the faint afterglow of old activity remaining. And yet the potential for violence still exists. The region holds everything necessary for renewed activity. Gas clouds drift closer, stars wander, stellar collisions send debris inward. Occasionally, astronomers observe a bright flash, a sudden eruption, a mysterious flare from the black hole's vicinity. We cannot predict these events, but we know they will continue. Sagittarius A is not dead. It is sleeping lightly. The contrast between calm and chaos becomes clearest when viewed through different wavelengths. In radio light, the black hole glows softly, surrounded by streams of gas and glowing arcs shaped by magnetic fields. In infrared, the stars dominate, bright, crowded, dynamic. In X-rays, sudden flares and bursts reveal the region's hidden turbulence. Each wavelength tells a different story, yet together they describe a region in delicate balance. One of the most striking truths about the galactic center is how long this balance can last. Even when matter falls inward, the black hole accretes it slowly. Even when flares erupt, they dim quickly. Even when stars collide, they do so in a vast, crowded dance that rarely disrupts the overall structure. The galactic center is both violent in detail and calm in the whole. From afar, it behaves like a quiet anchor, heavy, stable, ancient. Up close, it becomes a storm of motion, swirling gas, colliding winds, flaring plasma, and stars whipping through warped space-time. This duality makes the region one of the most fascinating environments in the Milky Way. It is a place where extremes coexist, where gravity sculpts serenity and chaos settles into stable orbits. As you drift farther inward in imagination, toward the swirling edge of the accretion flow, a new truth begins to reveal itself. Not everything near the black hole is destined to fall in. Much of it is redirected, heated, pushed outward. The dance of matter becomes a contest between gravity and energy, between collapse and escape. And quietly, another question rises from this tension. What are the mysterious structures that extend thousands of light years above and below the galactic center, glowing faintly in high-energy light? Now we move into Part 7. Part 7. What are the mysterious Fermi bubbles above and below the core? In 2010, telescopes detected two enormous structures rising from the galactic center, vast bubbles of energy extending tens of thousands of light years. Their edges glow faintly in gamma rays, suggesting a powerful event long ago, a surge of activity from Sagittarius A or a burst of star formation. They are remnants of a past eruption, a cosmic exhale that still lingers in the darkness. To picture the Fermi bubbles, imagine floating above the Milky Way and looking down at its luminous spiral arms. The galaxy would appear like a whirlpool of light stretching 100,000 light years across. But rising from its center, upward and downward perpendicular to the disk, are two immense symmetrical lobes. They stretch so far that if your eyes could see gamma rays the way they see starlight, the night sky would be dominated by these glowing towers of energy. They reach nearly half the diameter of the entire galaxy. These structures were first revealed through NASA's Fermi Gamma Ray Space Telescope, whose detectors are sensitive to the highest energy light in the universe. Gamma rays are produced by extreme processes, particle collisions, supernova shock waves, black hole jets, and the decay of energetic cosmic rays. When scientists mapped the gamma ray sky, they expected to see diffuse emissions from cosmic rays interacting with dust and gas. Instead, they uncovered two enormous cavities, clean, sharply defined, glowing faintly, and rising like twin chimneys from the galactic plane. Nothing else in the Milky Way looks like them. They are too large to be remnants of a single supernova, too symmetrical to be random, too energetic to be ignored. And so the question emerged: what could carve such colossal shapes into our galaxy? Two main theories eventually rose to prominence. The first involves our central black hole, Sagittarius A. Though it is quiet now, it may not have always been so. Black holes can enter feeding frenzies when conditions are right, when large clouds of gas drift too close, or when stars are disrupted by tidal forces. During these periods, an accretion disk forms, heating gas to millions of degrees and launching jets of energy into surrounding space. In active galaxies, these jets can drill holes through thousands of light years of gas, producing enormous lobes filled with hot plasma. It is possible, perhaps even likely, that millions of years ago, Sagittarius A entered such a phase. During this time, intense radiation and particles could have streamed outward along the galaxy's rotation axis, inflating two cavities of high-energy plasma. As these jets faded, the bubbles would remain, slowly cooling over millions of years. Their edges would continue to glow in gamma rays as energetic particles collided with the thin halo of gas surrounding the Milky Way. This idea paints the Fermi bubbles as relics of a sleeping giant's outburst. The second major theory focuses not on the black hole, but on the stars around it. The galactic center is rich in massive stars that live fast and die violently. If waves of star formation swept through this region in the past, forming thousands of massive stars in a few million years, the combined explosions of their supernovae could have pumped enormous energy into the surrounding gas. Their shock waves would have merged into a unified outflow, blowing hot plasma outward along the path of least resistance, perpendicular to the disk. In this view, the Fermi bubbles are monuments to ancient star formation, a signature of a long, quiet burst of stellar birth and death. The truth may involve both processes. Star formation and black hole feeding are intertwined. When gas flows inward, it can fuel both new stars and the central black hole. The Milky Way may have experienced a period of intense activity where both mechanisms contributed to a large-scale outflow, carving the bubbles into the galaxy's halo. But however they formed, the bubbles are extraordinary not just for their size but for their structure. Their edges are unusually sharp, almost too sharp for random cosmic processes. This sharpness hints at shock fronts, where hot plasma expands rapidly into cooler gas. Observations from the South Pole Telescope later discovered microwave emissions along these edges, revealing a second set of structures called the microwave haze, possibly part of the same cosmic event. X-ray observations from ROSAT and ARO-SITA have also detected faint structures that align beautifully with the bubbles, suggesting they are filled with extremely hot gas, tens of millions of degrees in temperature. Inside the bubbles, the matter is thin but energetic. Cosmic rays, high-speed protons and electrons, move freely within them. Some models propose that turbulence inside the bubbles reaccelerates these particles, keeping them energetic for millions of years. Unlike typical galactic processes, the bubbles appear insulated, separated from the surrounding halo by magnetic boundaries or shear layers that prevent rapid mixing. This isolation is part of what makes them glow so uniformly. It is as though the Milky Way's center released a breath of hot plasma, and the breath has remained suspended in the halo, slowly fading, still holding the shape of its origin. If you could drift inside one of the bubbles, the surroundings would be incredibly faint. There would be no visible light at all. You would feel as though you were inside an enormous empty room. Thin gas, high energy, glowing only in the most extreme wavelengths. The plasma would be so diffuse that a cubic meter might contain only a few dozen particles, but each particle would be moving at tremendous speeds. Turbulent magnetic fields would ripple through the space, unseen but powerful. Yet the bubbles are not static. Their shape is subtly evolving. Simulations show that hot plasma rises buoyantly through surrounding gas, slowly expanding over millions of years. The bubbles likely formed quickly, on timescales of less than 1 million years, but have lingered since, growing, fading, and cooling as they interact with the galactic halo. Their presence also tells astronomers something crucial. The Milky Way is still alive. Galaxies are not static. They breathe, they flare, they rest. The Fermi bubbles are a signature of this breathing cycle, a reminder that galaxies evolve through quiet periods punctuated by eruptions of energy. For Earth, the existence of the Fermi bubbles poses no danger. They are far above and below the galactic plane, and the energy they contain is spread thinly across enormous volumes. But scientifically, they reveal the Milky Way's recent past, a past where the galactic center was far more active than it is today. And they raise deeper questions. If such an event happened millions of years ago, could it happen again? Could Sagittarius A return to a state of high activity? Could new waves of star formation send shockwaves into the halo? The galaxy's history tells us yes, there will be future eruptions. The core will flare again. It may already be preparing for such a phase. Astronomers have observed clouds of gas drifting inward, each with the potential to feed the black hole or spark new star formation. The Fermi bubbles are reminders not only of past activity, but of future transformations. As you drift away from the bubbles in your mind and return focus to the galactic center itself, their faint glow fades, and another question comes into view, one that sits closer to the black hole, where orbits curve sharply and gravity dominates every motion. If the bubbles reveal the galaxy's past breaths, what secrets lie in the very motions of the stars at the center? What does gravity sculpt in the inner core? Now we drift quietly into Part 8. Part 8. How does gravity sculpt the stars near the center? The inner region of the Milky Way is shaped not just by the black hole, but by a dense sphere of stars, clusters, and dark matter all orbiting together. Their combined gravity creates a landscape unlike any other part of the galaxy, a place where paths curve sharply, where energies run high, and where stars live short, dramatic lives. Gravity there is not just a force, it is an architecture. To understand this architecture, imagine gliding slowly inward from the quieter outskirts of the galaxy. For tens of thousands of light years, stars drift in wide, calm orbits. The spiral arms rise and fall like gentle waves. But as you drift closer to the heart, the light thickens. The stars grow younger, brighter, and denser, almost as if you are approaching a city after traveling through rural land. The motions become less uniform. Space feels crowded. Gravity sharpens. By the time you enter the central few hundred light years, a region called the central molecular zone, the density of matter is astonishing. Clouds of gas tower above you in vast cold structures. Star formation erupts in bursts. Supernova remnants glow faintly in radio light. But the most dramatic change lies ahead. In the central parsec, the inner few light years around Sagittarius A. Here, gravity becomes a landscape of steep slopes and rapid curves. This is where gravity does more than attract objects. It sculpts their very existence. The central parsec contains several distinct stellar populations, each shaped by gravity in its own way. The first is the S-star cluster, a group of hot, young, massive stars that move in tight, rapid orbits around the black hole. These stars were discussed earlier, but now we see them as part of a larger, gravitationally sculpted system. Their orbits form a kind of inner shell or halo around Sagittarius A, each path carved by the curvature of space-time. Gravity is so intense here that Newtonian physics alone cannot explain their motion. General relativity is required to make sense of their trajectories. Around them lies the central star cluster, a crowded mix of old red giants, stripped stars, compact remnants, and hot blue stars. Their orbits form a swirling, complex structure, some aligned, some tilted, many eccentric. The gravitational floor beneath them is not flat. It is warped by the black hole, by the mass of the star cluster itself, and by the diffuse distribution of dark matter permeating the region. Dark matter, though invisible, plays a subtle role here. It contributes to the total gravitational pull, smoothing out the transitions between shells of stars, guiding them into long-term orbits that remain stable for millions of years. Though we cannot see it, its presence shapes the central gravitational field like a hidden scaffold. Farther out, in a region roughly 110 light-years from the center, lies something especially unusual, a flattened structure called the circumnuclear disk. This is a ring of gas orbiting the black hole, composed of clumps, filaments, and dense regions where new stars might one day form. This disk acts as a reservoir of future material that could drift inward, fueling either star formation or the black hole itself. Its orbit is highly influenced by the gravitational pull of the central cluster, and its outer edges feel the tug of the larger galaxy. Every layer interacts with the others. The stars pull on the gas pulls on the stars, dark matter pulls on everything, and the black hole shapes the entire ensemble with its deep gravitational well. This interplay creates a gravitational environment that is as intricate as it is extreme. Stars near the center live fast and die young. Massive stars formed in the dense environment burn through their fuel in just a few million years. They explode as supernovae, enriching the region with heavy elements, stirring turbulence in the gas and nudging nearby stars into different orbits. These explosions leave behind neutron stars and black holes, which themselves sink inward due to dynamical friction, a kind of gravitational drag caused by moving through a dense stellar environment. This creates what astronomers call a stellar cusp, a concentration of compact objects near Sagittarius A. Though most of them are invisible, their mass adds subtly to the gravitational shape of the region, altering the paths of the visible stars. Gravity here is layered like currents in a deep ocean. Another remarkable structure shaped by gravity is the population of hypervelocity stars. These stars were once part of binary pairs that wandered too close to the supermassive black hole. When the black hole ripped the pair apart, one star was ejected outward at immense speed, fast enough to escape the galaxy entirely. Their trajectories trace gravity's sharp edges, the way a stone flung by a sling carries the memory of tension in its path. Meanwhile, the surviving star from each disrupted binary remains trapped in a tight orbit around the black hole. These captured stars join the S-star cluster, adding new members over time. Their orbits, often highly eccentric, act as signatures of gravitational encounters long past. The gravitational environment also determines how gas flows. The central region is threaded with magnetic fields shaped by the distribution of mass. These fields channel gas into streams, filaments, and arcs that wind through the region like sculpted bridges. Some gas follows spiral infall paths toward the black hole. Some is swept into expanding shells by stellar winds. Some collects in dense pockets where gravity overcomes pressure, creating new stars. All of this structure, stars, gas, dark matter, responds to gravity's architecture and in turn reshapes it. Gravity is not static. It evolves as the distribution of mass evolves. When a supernova erupts, it alters the environment. When a star collapses into a black hole, the distribution shifts. When gas drifts inward, the gravitational field changes, even if subtly. In the central parsec, these shifts happen on timescales far shorter than those of the outer galaxy. Out in the spiral arms, stellar motions take hundreds of millions of years to change noticeably. Near Sagittarius A, a single human lifetime spans enough time for astronomers to watch stars complete significant fractions of their orbits. Gravity here moves quickly. It sculpts in real time. Yet for all this complexity, there is an underlying order. The orbits settle into families. The distribution of mass forms layers. The gravitational potential wells deepen smoothly toward the center. Even the apparent chaos of stellar collisions follows predictable patterns over long timescales. In this dense region, stars cannot expand into large red giants without having their outer layers stripped by tidal forces or collisions. This is why we see fewer red giants near Sagittarius A than predicted. They have been pruned away by gravitational interactions, leaving behind more compact, resilient stars. Gravity sculpts by taking away as much as it adds. It sculpts through constraint, through destruction, through motion, through equilibrium, and through time. As we drift through this environment in imagination, the Milky Way's center feels less like a violent battleground and more like a vast, ancient citadel of motion, shaped by forces too deep and too patient to be seen directly. Every star, every cluster, every arc of gas follows a path traced by gravity's geometry. And as we reach the edge of the black hole's sphere of influence, a new mystery emerges. Why do young stars, brilliant, short-lived, massive, appear so close to a place where star formation should be nearly impossible? Now we move gently into Part 9. Part 9. Why are young stars forming so close to danger? One of the deepest mysteries is the presence of young, massive stars orbiting near Sagittarius A. Their existence contradicts expectations. Star formation should be impossible so close to such intense tidal forces. Yet they are there, bright, hot, and newly born. Some theories suggest they formed farther out and drifted inward. Others propose they formed inside dense clusters that shielded them from tidal disruption. To understand just how strange these young stars truly are, imagine drifting through the innermost light years of the galaxy. Here, gravity is steep and unforgiving. Clouds of gas, normally the seeds of new stars, are stretched and sheared by the black hole's immense pull. Any cloud large enough to collapse into a star is torn apart long before it gets the chance. This should be a region defined only by survival, not birth. Yet when astronomers pointed infrared telescopes toward Sagittarius A, they found the unthinkable. Dozens of massive, luminous, short-lived stars shining boldly in a place where nature should forbid their existence. These stars, some 10 to 20 times the mass of the Sun, are young by cosmic standards, only a few million years old. They blaze hot and bright, pouring ultraviolet radiation into the surrounding gas. Their surfaces crackle with fierce winds that rush outward at thousands of kilometers per second. These are O-type and B-type stars, the universe's sprinters, living fast and dying violently. And the fact that they orbit so close to the black hole, some within mere tenths of a light year, is one of the most perplexing discoveries in galactic astronomy. The puzzle is known as the paradox of youth. By all logic, these stars should not be here. Star formation requires cold, dense clouds of molecular gas. In the galactic center, such clouds are shredded by tidal stretching. The closer you approach Sagittarius A, the more violently tidal forces tug on anything extended or diffuse. If you dropped a typical star-forming cloud into this region, the black hole's gravity would pull its near side with a stronger force than its far side, stretching it into filaments and dissipating it entirely. Nothing should collapse, nothing should condense. Star formation should be quenched. Yet the evidence glows brightly in infrared light. The stars exist anyway. So how did they get there? Astronomers have proposed several elegant but challenging solutions. Each reveals a different way nature might outmaneuver the black hole's tidal grip. Theory 1. The stars formed farther out and migrated inward. One possibility is that these young stars were born several light years away, in regions where tidal forces were weaker. Massive clusters can form in those outer regions, especially in the central molecular zone, where dense clouds occasionally collapse under their own weight. Over time, interactions with other stars and clusters, through gravitational nudges known as dynamical friction, could slowly drag these star clusters inward. This process would take millions of years, roughly the same amount of time as the star's current ages. But there is a problem. The orbits of the stars near Sagittarius A do not resemble the tightly packed structure of an infalling cluster. Instead of clustering closely together, they form two distinct populations, the tightly orbiting S stars and a larger, disk-like arrangement of massive stars orbiting farther out. If these stars were dragged inward as a single group, we would expect a more uniform structure. Still, migration cannot be ruled out completely, especially for the stars that orbit slightly farther from the black hole. Theory 2. The stars formed in a dense disk of gas around Sagittarius A. Another compelling idea is that these stars formed in place inside a massive disk of gas that once orbited the black hole itself. Imagine a rotating disk of gas, thick and heavy, swirling around Sagittarius A like water spiraling down a drain. If the disk were dense enough, and if the gas cooled efficiently, pockets of it could collapse despite the strong tidal forces. Gravity within the disk could overcome the stretching effect of the black hole, allowing stars to form directly within the harsh environment. Simulations show that such a disk could produce exactly the kind of stars we observe: hot, massive, and arranged in somewhat planar structures. This theory beautifully explains the presence of the clockwise stellar disk, a group of young stars that share similar orbital orientations, as though they inherited their motion from the rotation of the disk they were born in. The challenge with this idea is timing. If the disk existed a few million years ago and then dissipated, it would need the right conditions, enough gas to form stars, but not so much that it fueled Sagittarius A into a dangerous feeding phase. Yet the galaxy's history suggests exactly such episodes may have occurred. Theory 3. The Hills mechanism: binary stars torn apart. A third theory involves dramatic gravitational interactions. Binary star systems, pairs of stars orbiting each other, are common in the galaxy. If a binary wandered too close to the black hole, Sagittarius A could tear it apart. In such an event, one star is flung outward at tremendous speed, becoming a hypervelocity star, while the other is captured into a tight orbit around the black hole. This mechanism explains the existence of young stars in looping, elongated orbits. It does not explain the presence of the more organized stellar disk, but it beautifully accounts for the S stars near the very center. Their orbits are too random, too varied, too dynamically mixed to have formed in a disk. They behave exactly like stars that were thrown inward through violent gravitational encounters. But this mechanism does not create birth near the black hole. It creates relocation. It moves young stars inward, but cannot explain how they formed in the first place. Theory 4. Star clusters formed elsewhere, shielded by their density. Some astronomers propose that young stars formed inside incredibly dense star clusters farther out, clusters so tightly bound that the black hole's tidal forces could not tear them apart. These clusters would slowly migrate inward and dissolve as they approach Sagittarius A, leaving their youngest, most massive stars behind. This idea unites the concept of inward migration with the protective shielding of a massive cluster. It explains how star formation could occur in environments where gas is dense enough to resist tidal disruption. The difficulty is that no remnants of such clusters have been clearly identified, though some suspected candidates may have dispersed long ago. Why the mystery remains. Each of these theories explains part of the puzzle, but none explains everything, and the deeper astronomers look, the more complex the picture becomes. Some stars near the center are extremely young, only a few million years old. Some form a disk, suggesting Shared origin. Some do not, implying a separate history. Some show orbits so eccentric they must have been perturbed. Others show a coherence only possible from formation in place. It is likely that multiple mechanisms acted together. A burst of star formation in a dense disk, followed by migration, followed by gravitational scatterings layered over millions of years. The result is the strange, beautiful population we see today. What the presence of young stars reveals. These stars are not just anomalies. They are clues to the history of Sagittarius A. They show that the galactic center is not a static environment. It has cycles of activity, quiet periods, bursts of gas inflow, episodes of star formation, times when the black hole feeds more aggressively, times when it sleeps. The stars are fossils of these cycles, written in their motion, their age, and their alignments. Their presence tells us that the region near the black hole is more dynamic than we once imagined. It reveals that star formation can occur under conditions once thought impossible. And it reminds us that gravity, though powerful, is not absolute in its forbidding. With the right densities, the right temperatures, the right flows of gas, even the harshest environments can become nurseries. And as we drift quietly deeper into the galactic center, another question rises from the glowing arcs of gas spiraling inward. What happens to the gas that does not become stars? Where does it go as it approaches the black hole itself? Now we move into Part 10. Part 10. What happens to gas as it falls toward the black hole? Gas near the galactic center does not fall inward peacefully. It spirals, plunging into a violent dance of friction and heat. As it accelerates, it forms a swirling disk glowing in infrared and X-rays. Much of that gas never reaches the event horizon at all. It is blown outward, heated so intensely that it escapes. Only a fraction completes the journey and disappears into the dark. To understand what happens to this gas, imagine floating above Sagittarius A in perfect silence, watching from a safe distance. The space around the black hole is not empty. It is filled with drifting clouds, heated winds from massive stars, and thin filaments of dust woven through the inner parsec. These materials constantly pass near the black hole, yet only a tiny amount is captured. Most continues its motion around the galactic center, unaffected or only nudged by gravity. That alone is surprising. You might expect the black hole to behave like a cosmic vacuum cleaner, effortlessly devouring any matter that crosses its path. But black holes are not hungry mouths. They are deep gravitational wells. To fall inward, matter must lose angular momentum, the sideways motion that keeps it in orbit. As long as the gas continues moving around the black hole faster than it falls toward it, it will remain in orbit. But occasionally, some of this gas slows just enough to spiral inward. This is where the story changes. Once gas begins its inward descent, it enters a region where friction, pressure, and magnetic turbulence take over. The gas forms a loose, unstable structure known as an accretion flow, not a tidy, thin disk like the textbooks portray, but a puffed, chaotic, overheated volume of spiraling material. In the case of Sagittarius A, the accretion flow is especially inefficient. It emits heat, it loses mass through outflow, and it rarely collapses into a long-lived rotating disk. But even in this chaotic flow, certain principles remain the same. As gas falls inward, it speeds up. As it speeds up, it rubs against other gas. This rubbing, friction at cosmic scales, heats the material to extraordinary temperatures. The temperatures involved are staggering. Gas just outside the black hole can reach tens of millions of degrees. At these temperatures, electrons no longer remain bound to atoms. They tear free, creating plasma. This plasma emits energy across many wavelengths: infrared, from warm dust and cooler gas; X-rays, from the hottest regions closest to the event horizon; radio waves, from electrons spiraling along magnetic fields. This is why telescopes like Chandra, ALMA, and the Event Horizon Telescope are able to observe the galactic center at all. They do not see the black hole directly. They see the glow of this tortured plasma circling just outside its edge. But despite its brightness, the accretion flow of Sagittarius A is surprisingly inefficient. Only a tiny fraction of the gas that enters actually falls across the event horizon. Most of it is blown outward again, caught in turbulent outflows. Why does this happen? The answer lies in the temperatures and magnetic fields within the flow. When gas is heated to extreme temperatures, it expands violently. The thermal pressure becomes intense enough to counter gravity's pull. Magnetic fields, twisted by the motion of plasma, further accelerate particles outward. As a result, gas near the black hole behaves like steam bursting out of a pressure valve. This phenomenon is known as radiatively inefficient accretion. Sagittarius A, compared to more active black holes in other galaxies, is starved of fuel, and the fuel it does receive often escapes before it reaches the event horizon. This prevents the formation of the thin luminous accretion disks seen in quasars. Instead, we observe a dim flickering glow punctuated by occasional flares. When these flares occur, perhaps a few times per day, they provide a window into the mechanisms at work. A small clump of gas falls inward, compresses, heats, and emits a pulse of infrared and X-ray light. The flare fades as the clump either falls across the event horizon or is ejected outward by turbulence. These flares last for minutes to hours, but they reveal that even in its quiet state, the black hole is constantly interacting with its environment. The dynamics become even more interesting when gas arrives in larger structures. Consider the G2 cloud, a dusty object first observed in the early 2000s. As it approached Sagittarius A, astronomers expected a dramatic event, a bright flare as the cloud was torn apart and consumed. But instead, G2 survived, stretched but intact, and swung back outward. This surprising resilience suggested that G2 might not be a simple cloud, but perhaps a star shrouded in dust. This event showed that the accretion flow is more complicated and less predictable than models once suggested. Still, the intricate interplay between inflow and outflow defines the region. Closer to the event horizon, the picture becomes even more extreme. Gas must shed nearly all of its angular momentum to enter the black hole. This shedding occurs through friction-like processes, magnetic turbulence, and collisions within the plasma. These processes heat the material further, creating conditions where electrons and ions move at relativistic speeds, fractions of the speed of light. Particles in this region emit synchrotron radiation, a form of energy created when charged particles spiral around magnetic field lines. This radiation peaks in sub-millimeter wavelengths, which is precisely why the Event Horizon Telescope observes the black hole at 1.3 millimeters. That wavelength cuts through dust and reveals the final frantic motions of plasma on the edge of disappearance. Even as gas hurtles toward the event horizon, something surprising happens. It slows down, at least in appearance. From the perspective of a distant observer, gas approaching the black hole seems to freeze in place, its light stretched to redder wavelengths until it fades from view. But in its own frame of reference, the gas continues falling, crossing the event horizon in finite time. This dual perspective is a hallmark of relativity and contributes to the eerie stillness that masks the black hole's true motion. Some gas never gets this far. Magnetically driven winds can create outflows that send material tens or hundreds of light years away. These winds might contribute to the formation of structures like the galactic center lobe, or even play a role in the formation of the Fermi bubbles discussed in the previous segment. The interplay of inflow and outflow ensures that gas near Sagittarius A is never fully quiet. It is a balance point between collapse and escape, between feeding the black hole and enriching the surrounding environment. Over millions of years, the average inflow remains low, but the potential for change is always present. One dense cloud drifting inward could awaken Sagittarius A into a more active phase. This dynamic behavior reveals something fundamental. Black holes do not simply swallow, they sculpt their surroundings, and the environment responds in kind. The gas that avoids falling inward eventually mixes back into the surrounding medium, potentially contributing to future star formation or feeding other large-scale structures. The gas that falls inward disappears from our universe's visible fabric, carrying its mass, energy, and angular momentum into the singularity. What we observe from afar is not the fall, but the struggle. Gas pulled between two destinies, consumption or escape, creates the constant flicker of light that reveals the physics of the galactic center. And as we watch this battle play out across thousands of years, a new question emerges. How do we map something that cannot be seen directly? How do we draw the architecture of an object that emits no light, only influence? Now we turn, quietly and slowly, into Part 11. Part 11. How do we map something we cannot see? Sagittarius A cannot be photographed the way we photograph planets or stars. Yet in 2022, the Event Horizon Telescope gave us the first image of its shadow, a soft, blurry ring of light surrounding a dark center. That faint glow is matter on the brink of falling inward. From radio waves gathered across the Earth, scientists reconstructed a picture of a place where light bends, time slows, and gravity reaches its deepest form. To understand how such a picture was created, imagine trying to map a coastline hidden behind an endless fog. You cannot see the shore, but you can listen for waves, measure echoes, and infer the shape of what lies beneath. Mapping a black hole is similar. The object itself emits no light, no reflection, no surface glow. All it offers is the behavior of the space around it, distorted light, bent trajectories, and the frantic motion of matter spiraling into its grasp. The only way to see Sagittarius A is to study what happens near it, not on it. For decades, astronomers used indirect methods to understand its mass and size. By tracking the orbits of the S-stars, those fast-moving, eccentric stellar loops, we learned that a 4 million solar mass object must be hiding at the center. But this was still a silhouette painted by gravity, not an image of the black hole itself. To photograph something that emits no light required a new kind of telescope, one not built of glass lenses or polished mirrors, but built of data, timing, and global collaboration. This telescope would be the Earth itself, a telescope the size of a planet. The Event Horizon Telescope, EHT, is not a single instrument. It is a network of radio observatories scattered across the world, from Hawaii to Chile, from Spain to the South Pole. When these observatories tune to the same frequency and record the same signals from space, they effectively form one enormous telescope with a dish as big as the distance between them. This technique is called Very Long Baseline Interferometry, or VLBI. In VLBI, each telescope records incoming radio waves on its own, capturing faint signals with nanosecond precision. The timing of each wave crest is stored on atomic clocks, hydrogen masers, so precise that they drift less than a billionth of a second over many days. After an observing campaign, the data from each telescope are flown to central processors, where supercomputers combine them by matching the timing of the signals. When done correctly, the combined data reveal details as sharp as if they had been taken with a telescope the size of Earth. This kind of resolution is necessary because Sagittarius A is tiny on the sky, equivalent to seeing a donut on the moon. But radio interferometry brings an additional challenge. The image is not captured directly. What emerges first is a scatter of data, mathematical correlations rather than pixels. From that incomplete pattern, scientists must reconstruct an image through algorithms, careful, delicate work that requires both physics and art. The challenge of observing a restless black hole, Sagittarius A, introduces unique difficulties. In comparison to the black hole in the galaxy M87, also imaged by the EHT, Sagittarius A is smaller and more active. Matter swirls around it in minutes, not days. Its brightness flickers rapidly, meaning the image changes during the time it takes the telescopes to gather data. Creating a long exposure photograph of something that won't hold still is deeply challenging. Imagine trying to capture a clear picture of a candle flame in a windstorm. The flame shifts, stretches, twists. If you take too long, the photograph becomes a blur. That is what Sagittarius A presents, motion on timescales comparable to the observing window. To manage this, EHT scientists developed algorithms to piece together a kind of averaged image, one that captures the stable features of the black hole's environment while smoothing out rapid fluctuations. It required millions of simulated reconstructions, each tested against models of what relativistic accretion flow should look like. The final result was not a crisp, high-definition picture. It was a glowing ring with a darker center, blurred by distance, shaped by gravity. But within that blur was remarkable clarity, the unmistakable silhouette predicted by Einstein's general relativity. Why the ring appears. Zdaroni, the bright ring around Sagittarius A, comes from the last glimpses of light emitted by hot gas swirling just outside the event horizon. This gas forms the innermost portion of the accretion flow, radiating at millimeter wavelengths that the EHT is designed to capture. But the ring is not simply a physical structure, it is an optical effect, light bent around the black hole by gravity. Some of the light circles the black hole multiple times before escaping. This creates a kind of glowing halo known as the photon ring, a delicate boundary marking the place where gravity becomes strong enough to trap light in orbit. Inside the ring lies the black hole's shadow, not the event horizon itself, but the gravitationally lensed silhouette of the region from which no light escapes. It is larger than the event horizon, enlarged by the bending of light around it. The dark center is the closest we will ever come to seeing a black hole, mapping the invisible with more than images. Yet the EHT image is only one way to map Sagittarius A. Astronomers map the black hole in other ways, each one revealing a different layer of its structure. 1. Stellar orbits. The paths of stars near the black hole trace the gravitational field, allowing us to calculate its mass, its location, the smoothness of its gravitational well. S2's orbit provided the first major test of general relativity around a supermassive black hole. 2. Gas dynamics. Infrared and radio telescopes track gas streams and filaments as they swirl inward. These motions, when modeled, reveal the spin of the black hole, still uncertain, the orientation of the accretion flow, the presence of magnetic fields. 3. Polarization. The EHT can detect polarized light, light aligned by magnetic fields near the black hole. This allowed scientists to map the invisible contours of magnetic structures that guide the hot plasma inward and outward. In 2023, a polarized image of Sagittarius A was released, showing that magnetic fields near the event horizon are strong and organized, helping to shape the accretion flow's turbulence. 4. Flares. Sudden bursts of infrared and X-ray light reveal temporary hotspots, small orbits of gas whipping around the black hole before dissolving. These hotspots act like tiny test particles, tracing the very curvature of space-time. Each flare is a fleeting map of gravity at work. The black hole is an absence that shapes everything to map something invisible. We watch how it deforms everything around it. Light bends, orbits twist, gas heats, time slows. Sagittarius A is not seen directly, but its fingerprint is everywhere. Mapping it is like mapping the shape of a whirlpool by watching how leaves drift around it. Through these methods, interferometry, orbit tracking, polarization, flare monitoring, we build a layered, multi-dimensional portrait of the galactic center. Each method is incomplete alone. Together, they reveal the structure of the most extreme environment in our galaxy. And yet, even with these extraordinary tools, the black hole keeps some secrets close. Its exact spin remains debated, its magnetic fields shift unpredictably, its feeding rate varies, its long-term evolution is uncertain. But we are closer than ever to understanding the invisible. The EHT image was not the end, it was the beginning. And now, as we drift deeper into this quiet journey, another question arises from the edge of the shadow. If the black hole shapes the galaxy, what shapes the galaxy in return? What subtle pull does the Milky Way exert on the heart that anchors it? Now we move into Part 12. Part 12. Why does the galactic center influence the entire Milky Way? Though it occupies a tiny fraction of the galaxy's volume, the center shapes everything. Its gravity pulls on stars thousands of light years away. The distribution of gas, the orbits of stellar groups, even the direction of spiral arms, all respond to the long, slow rhythm of the central mass. The core is not a distant curiosity. It is the gravitational heart that keeps the Milky Way coherent. To appreciate this influence, imagine the Milky Way not as a collection of isolated parts, but as a single, interconnected system. Every star, every cloud of gas, every spiral arm is moving in response to the galaxy's total mass distribution. And at the very center, deep beneath layers of stars wrapped in dust, surrounded by hot plasma, lies the heaviest concentration of matter in the entire system, a supermassive black hole, a dense nuclear cluster, a tightly bound bulge of billions of stars. Together, these components form a gravitational anchor that holds the galaxy's structure in place. Without this central mass, the Milky Way would not look the way it does. Its shape, its symmetry, its rotation, all would unravel. The gravitational heart of the galaxy. At the most basic level, gravity determines how stars orbit. The stars in the disk, including the Sun, move in immense circular paths around the center, but these paths are not shaped by the visible spiral arms. They are shaped by the galaxy's gravitational potential, a smooth field carved by all of its mass, concentrated heavily toward the core. When we orbit the galaxy every 225 to 250 million years, we are not orbiting empty space. We are orbiting the center. Even though Sagittarius A accounts for only a small fraction of the Milky Way's total mass, about 1 part in a billion, it sits at the bottom of the gravitational well that everything else responds to. Surrounding it is the central bulge, containing perhaps 10% of the galaxy's stars. This collection of old metal-rich stars forms a massive spheroidal structure. Together with the black hole, it creates a gravitational centerpiece that stabilizes orbits far beyond the inner regions. The spiral arms themselves, the great sweeping features that define our galaxy, owe their persistence in part to the gravitational field set by the bulge. The core, in a sense, conducts the galaxy's rotation. The influence of the bar deep inside the Milky Way, the central bulge, is not perfectly round. It extends into a long, boxy structure known as the galactic bar, a stretched arrangement of stars that rotates like a slow cosmic lever. This bar acts like a gravitational engine, driving the flow of gas and shaping the motion of stars across tens of thousands of light years. The bar funnels gas inward, compressing it into the central molecular zone, where dense clouds gather and new stars occasionally ignite. This inward flow helps feed the region near Sagittarius A, influencing episodes of star formation and black hole activity. But the bar also shapes the outer galaxy. Its rotating mass creates resonances, regions where gravitational patterns enhance or suppress motion. These resonances help define the locations of spiral arms. They organize the orbits of stars. They create the galaxy's overall pattern, as though sculpting order from a sea of motion. Without the bar and bulge, the Milky Way's spiral arms would lose their coherence. The galaxy would become more diffuse, its structure softened. How the center shapes the flow of gas in the galaxy does not move freely. It follows gravitational contours like rivers following terrain. In the Milky Way, these flows converge toward the center. As gas moves inward under the influence of the bar and bulge, it encounters density waves, which form the spiral arms' shock fronts, where gas compresses and forms stars' resonances, where orbital speeds shift. Ultimately, much of that gas ends up near the galactic center, where conditions become extreme. This inward flow feeds cycles of star formation, wind generation, and the occasional flare of black hole activity. Think of the Milky Way as a living system. Gas circulates, stars are born, stellar winds push outward, gravity pulls inward. The core orchestrates that circulation, the deep gravitational well. Even stars far from the center feel its pull. Our Sun, 26,000 light-years away, traces a path around the galaxy dictated by the total enclosed mass, including the bulge and the black hole. Without this stable central mass distribution, the Sun's orbit would wobble, drift, or become irregular over billions of years. Galactic stability requires a strong gravitational anchor. That anchor is the core. It is only because of this anchor that the Milky Way maintains its flat, rotating disk. If the central mass were significantly smaller, the galaxy's structure would loosen. If larger, the disk would tighten and rotate differently. Every star's motion depends on the weight at the center. Even dark matter, the invisible halo surrounding the galaxy, interacts gravitationally with the core. The halo shapes the galaxy's large-scale rotation curve, but the central mass defines the fine structure of stellar motion. Why the black hole matters for the whole galaxy, Sagittarius A is small compared to the bulge, but its influence is precise. It shapes the very inner gravitational field, ensuring the bulge remains compact, stable, and centrally concentrated. Without a supermassive black hole, the nuclear cluster might expand and disperse, the bar's rotation would shift, gas inflow would change dramatically, the bulge might flatten or distort. The black hole provides a gravitational pin at the center, ensuring the surrounding structures remain in place. It is the point around which the galaxy balances, quietly holding the inner light years together. Even though most stars will never come close to it, they all orbit in response to its presence and the dense mass around it. The core, as a driver of long-term evolution, galaxies evolve over billions of years. Their shapes and motions change slowly, influenced by mergers, gas accretion, stellar death, and feedback from black holes. The activity, or quietness, of the galactic center plays a role in this evolution. When Sagittarius A was more active millions of years ago, its outflows likely influenced the halo, creating structures like the Fermi bubbles. Energetic winds from the center may have cleared gas from certain regions, affecting future star formation. Quieter periods allow gas to drift inward again, setting up cycles of activity. In this sense, the galactic center acts like a regulator, sometimes releasing energy, sometimes collecting it, always shaping the long-term destiny of the galaxy. The center keeps the galaxy coherent. It is easy to imagine the Milky Way as a static picture, spiral arms firmly in place, the disk rotating endlessly. But the reality is a dynamic, ever-changing system. Stars die, gas moves, clusters dissolve, spiral arms shift. Through all of this, one thing remains constant: the gravitational pull of the center. Without the core, the Milky Way would unravel slowly. With it, the galaxy retains its shape, its rhythm, its identity. The core is the quiet stabilizer of cosmic time. A quiet question as we drift deeper, as you imagine the Milky Way not as a flat image, but as a living structure shaped from the inside out. A new thought begins to settle. If the center shapes the galaxy and the galaxy shapes the center, what happens when these forces change? What happens when new stars form, or when gas falls inward, or when the black hole awakens again? The next chapter brings us closer to that question, toward the history of our galaxy and the long, quiet cycles written in its core. Now we move into Part 13. Part 13. Could Sagittarius A ever become dangerous to us? For now, and for millions of years, the black hole's influence on Earth is gentle, a distant anchor. But astronomers wonder what would happen if a star wandered too close, or a gas cloud triggered a bright feeding episode. Historical evidence hints that Sagittarius A has flared before. If it did again, the light would wash across the galaxy long before any physical danger reached us. To explore this question, imagine the Milky Way as a vast rotating city of stars and Sagittarius A as a quiet monument at its center. From our vantage point, 26,000 light-years away, we are far beyond the reach of the black hole's direct gravitational pull. Our orbit is shaped by the mass of the entire galaxy, not by the black hole alone. In that respect, Sagittarius A is harmless to us. Its gravity does not tug on our sun, it does not shift Earth's orbit, it does not influence our tides or our seasons. But black holes are not defined only by gravity. They can also release energy when they feed. And this is where the question deepens. Right now, Sagittarius A is in a prolonged state of quiet. It consumes very little. The accretion flow around it is sparse, thin, and radiatively inefficient. The black hole glows faintly in radio and infrared light, flickering occasionally. when a small clump of gas spirals inward. These flares are minor events by cosmic standards, nothing that would ever reach Earth in harmful form. Yet the galaxy's past suggests that Sagittarius A has not always been so calm. A quiet giant with a fiery history, astronomers have found clues that the black hole was far more active a few million years ago. The most dramatic evidence lies in the twin structures known as the Fermi bubbles, immense lobes of gamma rays rising above and below the galactic plane. These bubbles likely formed from a major outflow of energy, either from a burst of star formation in the central region or from a period when the black hole accreted far more material than it does today. Another clue comes from X-ray reflections on nearby molecular clouds. Some of the giant gas clouds near the galactic center shine with reflected X-rays, as though illuminated by a bright flash that occurred hundreds of years ago. These clouds act like cosmic mirrors, preserving the memory of an event we did not see directly. They suggest that Sagittarius A may have flared to millions of times its current brightness in the relatively recent past, perhaps due to the disruption of a star or a sudden inflow of gas. Even so, none of these historical episodes threatened Earth. The energy, though immense, was spread across vast distances. By the time it reached us, it was diluted into background radiation. Still, these hints raise a real question. What if Sagittarius A flared again? What could trigger a future flare? Several scenarios could awaken the black hole. A star could wander too close. If a star passed within a few tens of astronomical units of the event horizon, the black hole's tidal forces could tear it apart, creating a tidal disruption event. The shredded star would form a bright, hot accretion disk, glowing intensely for months or years. A dense gas cloud could fall inward. Large molecular clouds occasionally drift near the center. If one fell deep enough into the black hole's gravitational well, its gas would compress, heat, and ignite with radiation before disappearing. A cluster of objects could collide near the core. Stellar remnants, black holes, neutron stars, collect in the center. Their interactions could send debris inward, long-term cycles of galactic evolution. Just as the Milky Way has quiet phases, it also has active ones. Over millions of years, inflows of gas from the bar or spiral arms can reignite central activity. Any of these could lead to a bright outburst, but even in the most extreme cases, the black hole's energy would be released as light, particles, and radiation, not physical debris. And because we are so far away, even powerful outbursts become gentle by the time they reach Earth. To us, they would look like a brightening of the galactic center, visible only to telescopes. What Earth would experience? If Sagittarius A entered a high-activity phase, Earth would not feel heat or pressure. Space is too empty, distances too vast. What would arrive are photons, light, radio waves, infrared glow X-rays, and gamma rays, heavily diluted fast-moving particles scattered by magnetic fields long before reaching us. Most of this radiation would be absorbed by the interstellar medium, weakened by dust and gas, and further reduced by Earth's atmosphere. A major flare might look impressive to astronomers, but for life on Earth, it would be insignificant. Earth has weathered supernovae closer than Sagittarius A, and even they left little lasting impact. What cannot happen? It is worth clarifying what Sagittarius A cannot do to Earth, no matter how active it becomes. It cannot suck in the solar system. It cannot disrupt Earth's orbit. It cannot trigger geological events. It cannot strip the atmosphere at this distance. It cannot eject jets that reach us with dangerous energy. Even the most powerful jets from active galaxies, the kind we see in quasars, narrow into beams only over short distances. By the time they extend tens of thousands of light years, they disperse. And Sagittarius A does not currently produce such jets. In short, we are safe from the black hole's direct influence, the psychological impact of a flare. Although Sagittarius A poses no physical risk, a bright flare would be a profound discovery. The entire astronomy community would witness the awakening of our galaxy's central black hole, a rare event unfolding in real time. We might see a sudden brightening in X-rays, a surge of infrared light, new structures in the accretion flow shockwaves traveling through central gas clouds, It would offer an unprecedented window into black hole physics. But beyond the scientific impact, the emotional effect could be powerful. The knowledge that our galaxy's heart had stirred would ignite wonder, curiosity, and perhaps a gentle unease. It is not danger we would face, but a reminder of our place in a vast evolving system, long-term risks over unimaginable timescales. While Sagittarius A is harmless on human and even civilizational timescales, we can look farther ahead, millions to billions of years. Over such epochs, stars may be scattered by gravitational interactions. Gas could accumulate and trigger renewed activity. The Sun will continue orbiting the galaxy, passing near regions of varying density. Even so, Sagittarius A is unlikely ever to pose danger to Earth. Long before any conceivable threat, the Sun itself will evolve into a red giant, reshaping our solar environment entirely. The galaxy's processes unfold slowly compared to the life cycle of stars. In cosmic terms, Sagittarius A is a distant giant whose storms never reach us. A quiet question at the end of the spiral. As we drift back from the center, one truth becomes clear. The black hole is a quiet companion, not an enemy. Its power is immense, yet its reach is limited. It shapes the galaxy but does not threaten us. Still, understanding its history and potential reminds us that the Milky Way is alive, evolving, and capable of extraordinary events. And as we contemplate these possibilities, another question rises in the quiet. If the black hole can flare, sleep, and awaken again, what does that reveal about the long-term fate of our galaxy? Now we move into Part 14. Part 14. What secrets lie in the stars that orbit closest? Some stars near the center follow incredibly elongated orbits, swooping close to the black hole before soaring outward again. These trajectories act like probes, measuring the exact shape of spacetime. In 2018, the star S2 revealed the redshift predicted by Einstein as it passed the black hole. With each orbit, these stars refine our understanding, tracing gravity's curve with perfect silence. To appreciate the importance of these stars, imagine drifting into the central parsec, the innermost few light years of the Milky Way, where gravity deepens sharply and motion becomes a kind of cosmic handwriting. In this region lies a small cluster of stars whose behavior is unlike anything else in the galaxy. They move fast, they move erratically. Their paths warp through space-time like brushstrokes on an invisible canvas. Astronomers call them the S-stars, and together they form one of the most extraordinary natural laboratories ever discovered. These stars are young, blue, and massive, rare traits so close to the black hole. Many follow elongated, eccentric orbits, stretched into long loops that bring them dangerously close to Sagittarius A every few years or decades. When they approach the black hole, they reach astonishing speeds, some exceeding 7,000 kilometers per second. Then, as they slingshot around the invisible mass, they fly outward again, like comets drawn into and expelled by a gravitational cathedral. Each orbit tells a story, each loop is an experiment, each passage is a measurement of spacetime. S2, the star that tested Einstein. Among all the SE stars, one holds special significance: S2. S2 orbits the black hole once every 16 years. Its path is highly elongated, bringing it within about 120 astronomical units of Sagittarius A, 3 times the distance of Neptune from the Sun. At that distance, the star is deep inside the black hole's gravitational field. Its velocity peaks at nearly 3% of the speed of light. In 2018, as S2 made its closest approach, astronomers monitored its motion and its light with unprecedented precision. The result was a clear measurement of gravitational redshift, the stretching of light caused by intense gravity. As S2 dipped into the curved fabric of spacetime, the wavelengths of its emitted light lengthened, shifting toward the red. This was not an artifact, not an interpretation. It was a direct observation of Einstein's theory of general relativity operating in the real universe, near a supermassive black hole. This single observation confirmed predictions that had remained untested. For decades, But S2 is not alone, the ballet of high-speed stars. Other stars, S38, S55, S62, S102, follow even more dramatic trajectories. Some have orbital periods as short as 10 years. One, potentially emerging from ongoing observations, may orbit in less than 10. These stars dive close to the black hole, looping through regions where space-time bends steeply. Their orbits precess, their paths shift slightly with each revolution. This precession, similar to the subtle motion of Mercury's orbit around the Sun, is caused by the curvature of space-time. In Newtonian gravity, their orbits would repeat perfectly, like closed ellipses. But in reality, the ellipses rotate over time, opening into rosettes, gravity's signature etched in motion. By tracking these shifts, scientists measure the mass of Sagittarius A, the distribution of matter around it, the presence or absence of unseen companions, the exact geometry of space-time near a supermassive black hole. Each star becomes a tool, a probe, carved by gravity to reveal gravity. What the closest stars tell us about the black hole. The orbits of the S-stars give us three foundational insights. 1. The black hole's mass is extremely compact. If the central mass were spread out, like a cluster of dark objects instead of a single black hole, the star's orbits would wobble in characteristic ways. They don't. Their motion demands a single, dense object. The measured mass, about 4 million suns, must fit within a region no larger than the orbit of Mercury. The only known physical object capable of such density is a black hole. 2. The black hole may have a moderate spin. Although the exact spin of Sagittarius A is still uncertain, subtle shifts in stellar orbits may eventually reveal it. A spinning black hole drags spacetime with it, a phenomenon called frame dragging or the lens-Thirring effect. Over decades, this dragging should be detectable in the innermost stellar pathways. We are on the brink of measuring this effect. 3. There may be unseen objects hiding near the core. The motions of the S-stars hint at the possible presence of compact remnants, stellar mass black holes, neutron stars, clusters of dark matter. These objects subtly perturb stellar paths. The more precisely we measure these orbits, the better we can map the unseen mass near the core, a region defined by precision and chaos. Observing these stars is a monumental challenge. The galactic center is shrouded in dust, visible only in infrared wavelengths. The stars are packed so tightly that distinguishing them requires instruments with exquisite resolution. The development of adaptive optics, technology that corrects for atmospheric distortion in real time, made these observations possible. Before adaptive optics, the stars near the center were indistinguishable smudges. Today, we can track their movements with millisecond precision, watching tiny shifts that reveal the whisper of gravity itself. Each night of observation adds a new point in a years-long curve. Each curve sketches a new insight. Each insight inches us closer to a clearer understanding of the galactic center. The mystery of the missing red giants. As we look at the orbits of the innermost stars, another puzzle emerges. The region near Sagittarius A is strangely sparse in red giants. These older, swollen stars should be present in large numbers, yet many are missing. Why? There are several possible explanations. Tidal stripping. Red giants are large and fragile. The black hole's gravity may tear away their outer layers. Stellar collisions. In this crowded region, stars may collide, shredding red giants and leaving behind more compact remnants. Past bursts of star formation. Young stars dominate because the region recently formed new stars in a dense disk. Whatever the reason, the absence of red giants highlights the extreme conditions shaping the inner light years. Hypervelocity stars. When orbits break, some stars do not remain bound. When a binary star system wanders too close to Sagittarius A, the black hole can tear the pair apart. One star is flung outward at extreme speed, perhaps over 1,000 kilometers per second, becoming a hypervelocity star expelled from the galaxy. The other remains trapped in a tight orbit, joining the S-star cluster. These violent exchanges trace the deep gravitational tides at the black hole's edge. Each ejection is a signature of interaction. Each captured star is a fossil of a disrupted past. The stars as storytellers taken together, the S-stars tell a story of formation under unusual conditions, migration influenced by tides, collisions in crowded environments, gravitational sculpting, the unfolding of general relativity in real time. Their movements are not random. They are the result of millions of years of gravitational influence. To watch them is to watch the heartbeat of the galactic center. Every time one loops through periapse, its closest point to the black hole, the galaxy's deepest physics is put on display. What future orbits may reveal. As more stars complete their orbits and as new observational campaigns continue, we will learn whether the black hole's spin twists space-time, whether unseen masses cluster in the core, whether dark matter plays a role near the event horizon, whether some stars are on the brink of being ejected, whether new stars are forming in the inner disk. Future instruments, such as the Extremely Large Telescope, ELT, will track these stars with even finer precision. Over the coming decades, we will observe complete orbits of many more S-stars. Their trajectories will become one of our clearest windows into the nature of gravity. A soft question rises as we drift gently back from the inner core. Watching these stars carve their loops in silence, a quiet thought emerges. If the stars near Sagittarius A reveal so much about gravity, what might the black hole's past and future whisper about the fate of the entire galaxy? Now we slip into Part 15. Part 15. What does the Milky Way's center reveal about the fate of galaxies? The quiet heart of the Milky Way is a window into the future of galaxies everywhere. Black holes grow, stars drift inward, orbits evolve, and over billions of years the balance shifts. By studying our own galactic center, we glimpse the long, slow evolution that shapes the cosmos, how galaxies live, how they change, and how they eventually fade into quieter forms. When you imagine a galaxy, you might picture swirling arms, glowing stars, and clouds of dust lit from within. But beneath the visible beauty lies an engine, an interior process that develops over cosmic time. The galactic center, with its deep gravity and its ancient history, reveals how these processes unfold. It is the archive of a galaxy's past, the governor of its present, and a preview of its future. To understand what the Milky Way's center teaches us about the destiny of galaxies, we must drift slowly through the layers of time and motion embedded there, past the violent birth of stars, past the flickering of gas falling inward, past the long orbits of S-stars into the deeper timescale of galactic evolution. The center as the memory of formation. Every galaxy begins as a cloud, vast, turbulent, collapsing under gravity. As these clouds condense, the densest regions light up with new stars. Over millions of years, the gravitational well at the core deepens. The first clusters fall inward. The first black holes merge. Over cosmic ages, the center becomes a dense, crowded sphere, filled with the remnants of early generations of stars. The Milky Way's central bulge holds these memories. Its stars are old, metal-rich, and ancient witnesses to the galaxy's earliest epochs. Their compositions reveal that the inner galaxy formed quickly, in bursts of rapid star formation. These early stars enrich the region with heavy elements, carbon, oxygen, iron, building the chemical foundation from which later generations arose. This is not unique to the Milky Way. It is true for spiral galaxies across the universe. The center tells the story of how galaxies begin. The quiet growth of supermassive black holes. At the core of most galaxies lies a black hole, small in size, enormous in mass. How these black holes formed remains a central mystery. Some were born from the collapse of early massive gas clouds. Others grew from mergers of stellar mass black holes. Some may even have formed through exotic mechanisms in the early universe. But once a supermassive black hole exists, its growth is slow and cumulative. It consumes gas drifting too close. It swallows stars that wander into its tidal reach. It merges with other black holes when galaxies collide. It collects matter during periods when inflows surge. Sagittarius A is quiet now. accreting little. It grows at a pace so slow it is almost imperceptible. But over billions of years, even this slow growth shapes the galaxy. Galaxies with more massive central black holes show different patterns of star formation, different bulge properties, different histories of gas inflow and outflow. From our black hole, we learn that galaxies grow inward as well as outward. The core regulates star formation. Galactic centers often act as regulators. When gas flows inward, it can ignite bursts of star formation. These bursts produce massive stars that live fast and die violently as supernovae. Their explosions enrich the galaxy with heavy elements while stirring turbulence that can either compress gas into new stars or push gas outward, slowing star formation. This cycle repeats over millions of years. Gas flows inward. Stars form in dense clusters. Winds and supernovae erupt. Gas is pushed outward or heated. The black hole sometimes awakens. Activity dies down. Gas accumulates again. The Milky Way's center shows signs of these cycles. Dense young clusters near the black hole, older stars that hint at past bursts of star formation, faint echoes of past energetic events preserved in molecular clouds. The Fermi bubbles, proof of a dramatic outflow millions of years ago. By studying these clues, astronomers reconstruct the heartbeat of our galaxy's history, and in doing so, uncover the universal rhythms of spiral galaxies. The center predicts the galaxy's long-term evolution. On timescales beyond human comprehension, galaxies transform. They grow through mergers, collide with smaller companions, exchange gas with intergalactic space, and gradually shift from star-forming systems to quieter, more diffuse structures. The Milky Way is no exception. In a few billion years, it will merge with the Andromeda Galaxy. When that happens, the centers of the two galaxies will spiral toward each other. Their stars will intermix. Gas flows will ignite bursts of star formation, and eventually, the two supermassive black holes will merge, releasing gravitational waves across the universe. This future is written in the physics of the center. The way Sagittarius A interacts with gas today offers a preview of how black holes shape merging galaxies. They can trigger quasar-like bursts. They can launch jets that sweep gas from the galactic center. They can quench star formation by heating interstellar material. Or they can trigger new stars through compression. By observing our own center in its quiet state, we learn what a galaxy looks like between such dramatic events. We see the calm between ancient storms, the quiet phase that many galaxies experience for most of their lives, the slow settling into cosmic quiet. As galaxies age, they gradually lose the ability to form stars. Gas becomes scarcer. The brightest stars burn out. Over tens of billions of years, the Milky Way will become a quieter, dimmer place. The galactic center reveals how this fading begins. Gas is funneled inward, but often expelled by stellar winds. Star formation becomes inefficient. The black hole's outflows heat surrounding regions. Massive stars die faster than new ones form. Slowly, the galaxy's luminous population declines. The center becomes a place dominated by long-lived cool stars, red dwarfs and remnants. The bright, hot O-type and B-type stars that once lit the spiral arms disappear. Star clusters dissolve. The bar weakens. Spiral arms fade into a gentle, ghostly swirl. Sagittarius A eyes will remain, increasingly dominant compared to the dimming galaxy around it. It will be one of the last sources of energy in the Milky Way's slow twilight. The center as a teacher of fate. Everything we observe in the galactic center, its quiet black hole, its tightly bound stars, its remnants of past activity, reveals how galaxies evolve. They begin with bursts of formation. They stabilize into long-lived structures. They undergo cycles of inward flow and outward feedback. They face mergers that reshape them. They gradually quiet into dimmer forms. The Milky Way's core is not unique in this, it is typical. By understanding our own center, we learn the life cycle of galaxies across the universe. We learn how structure emerges from chaos, how black holes influence evolution without dominating it, how stars flow through patterns set billions of years earlier, how galaxies breathe, age, and slowly settle. A final quiet truth hidden at the center. As we drift away from the galactic heart and imagination, one last understanding emerges. The center of the Milky Way is not simply a place, it is a story, an unfolding narrative that will continue long after our sun fades. The secrets written in its stars, its gas, and its gravity are the same secrets shaping galaxies throughout the cosmos. And as we turn the page toward the final part of this journey, one question remains softly in the dark. If the galaxy's center tells the story of how galaxies evolve, what does it tell us about our place within that story? Now we drift gently into the outro when you are ready.